we have one of the leading supplier of LPCVD based solutions for TOPCon, which is from Laplace. We have Josua Stückelberger, who is R&D manager Europe at Laplace. He's going to talk about the role of LPCVD and thermal processing tools in wider deployment of TOPCon. Joshua, the floor is yours.
So yeah, thank you very much for this kind introduction. Let me quickly share the screen. Can you see this?
Yes.
Oh, perfect. Thank you very much. So my name is Dr. Josua Stückelberger. I'm working with Laplace Renewable Energy Technology, and I want to introduce here a bit Laplace because I think in Europe and outside of China, we're not yet very well known, and to talk about the role of LPCVD and the thermal processing tools in wider deployment of TOPCon. So we are founded 2016. It's quite a young company in Shenzhen, China. And we were really believing in this N-type technology from the beginning, and therefore also pioneering TOPCon for mass production. We designed our equipment for this transition to TOPCon, and we have now over 3,700 people working already with a very strong focus on R&D, with about 400 people in it. In these last years, we were now heavily involved in bringing TOPCon to the mass production with over 200 gigawatts of equipment that is now delivered. And we also start now to step outside of China with 18 gigawatts already installed, like Vietnam, Malaysia, and now also entering to the US. Our biggest project that we have delivered so far was a 30 gigawatt plant or manufacturing plant. And I would like to also point out here again that within these years now, we have gained extensive experience in the manufacturing of TOPCon technology, and we have over 1,000 people working in the support of such manufacturing lines and gaining this experience. Even though you might not have heard of Laplace so far, you definitely have heard of some of our customers like Jinko Solar, LONGi, IcoSol, Jollywood, what we have heard just before now. So many of the big manufacturers are using our equipment in their TOPCon lines. When we say we are now also stepping out of China, we have now opened offices in Europe with Athens and Montpellier, and also the US with Silicon Valley, and Southeast Asia, as mentioned, or Hong Kong, Taiwan. This I'm quite proud of. So this short history, we already managed to be part of 15 world records, including the current of 26.89% efficiency, which was manufactured with the help of our equipment. And this, I think, is very impressive. So we can really show that our equipment is able to reach cutting edge technology and can be on the front runners. So what we having as equipment, so one of our flagship is a heat treatment system. So on the boron and phosphorus diffusion, where we have on the boron side already delivered over 450 machines and about 60% market share, whereas on the phosphorus side, we have about 350 machines delivered. Here the market share is of Laplace in the whole TOPCon market. We also have our deposition systems where we focus on LPCVD, especially due to the in situ oxidation. And here we delivered so far 650 machines and have a market share of around 50%. While for the back contacted side with TOPCon, here we have a market share of 100%. And we have ALD and PECVD systems where we delivered so far over 500 machines. Another big important part is the automation, especially now that everything moves to larger and thinner wafers. We have put big effort to get this running smoother. And since we can do the full automation for a turnkey solution, we can now better optimize it between the different systems. And we also have on the module side an equipment that is for reflective film layout. Here we can increase the module power in a glass-to-glass module by about 5 watt peaks. And we delivered already over 200 machines with about 90% market share. So what was it that drive Laplace and helped to really provide the new solutions to help TOPCon thrive? Here, I would like to mention a few innovations that Laplace has made. One is that we place our wafers horizontally in the systems. Then we also introduced the BCl3 as a precursor gas. And we designed our unique heating elements and also had with our double petal quartz tube to reduce the quartz usage. Last but not least, we work on a platform design, which allows our customer to be very customized on their needs for their different cell processes. So let's quickly talk about this horizontal wafer placement. Here, as most of you know, that standardized it is on a vertically, the wafers are vertically placed. We can reach a much better process uniformity and especially also use trays much more efficiently and therefore increase the capacity by placing the wafers horizontally. This leads to a cost saving of around 20%, and we get a much lower wafer sticks or breakage issues in the systems. And this is even supported by what we call a soft landing when we load and unload. And like this, we can use for the larger and even thinner wafers and could increase yield by about 1%. And as mentioned, a cost reduction of around 20%. We also pioneered this BCl3 transition. So here, when we moved from PERC to TOPCon, one of the big issues was the boron diffusion and to get good homogeneities in large batches and reproducibility. By using BCl3 as a gas source, we could lower the consumption, and we also could lower the byproduct B2O3, which significantly lowers the maintenance for the quartz parts. And with these two effects, we were able to reduce the operating costs for the boron diffusion by 70%, which was a big driver to make the TOPCon possible, or at least economical. The other one point that I want to mention is the heating element. And here we talk again about getting uniformity over large batches. And this also then in return increases the quartz lifetimes and the utilization space of the tube. And thanks to a better control of different elements within the tube, can also use shorter process times and getting therefore the productivity up. And the other one that I was mentioning was double petal quartz. Here we work again on the lifetime of our quartz material. So we invented a double petals so that we don't have any direct contact between the tubes and the boats. And this increased the lifetime of the quartz parts significantly. We also additionally could improve the space utilization again and all the uniformity as we get a better control of the gas flow within our systems and therefore also of the homogeneity of our depositions or diffusions. And all of this then brings down the OPEX. Let's have a look now at the typical TOPCon process flow. So we can see here that Laplace can provide all the equipment, the layer forming processes, as well as full automation in between them. And when we work together with suppliers for the wet chemistry and the metallization, and therefore then we're also able to provide full turnkey solutions. As mentioned earlier, we were pioneering the TOPCon for mass production, getting the LPCVD and the boron diffusion performances up to be competitive. And now we can say that it's a mature and well-established technology, and we can reach very high efficiencies for the silicon solar cells. We reach about 580 to 585 watt peaks, which is about 30 watt peaks higher than a PERC module when we use 72 full cells modules. I also would like to point out that our processes are optimized for an ideal interplay between all the different systems. Since we can provide the full deposition technology for the full line, we can really reach the highest final performance by optimizing all this interplay. And also by providing the whole automation for the full line, we can really reduce the breakage rate and improve the yield. As I've seen before, there are other methods to do the TOPCon line rather than LPCVD. There is mainly PECVD and PVD, as we have just heard now in the presentation before. So PVD so far is only adopted by one manufacturer, and LPCVD and PECVD is currently sharing the rest more or less equally between them. And we can also see that between LPCVD and PECVD, there's very little change in the process flow. While on the LPCVD side, we do the deposition in the intrinsic state and then do an ex situ phosphorus diffusion before the anneal. In the PECVD, we have an in situ or morphosilicon deposition, which is then still followed by an anneal. And both of them have wraparound and therefore need a wraparound removal. While the PVD can live without this, but still needs to get to the wet chemistry afterwards for a clean. When we now compare LPCVD and PECVD a bit more in detail, we can see that on the deposition rate, the PECVD is with over 10 nanometer per minute favorable, while LPCVD we can reach up to 8 nanometer per minute. When we then look at the wafers per hour, they are on a single loading. The PECVD is in a similar range with 4,200 versus 4,300 for the LPCVD. But I would like to mention here that we are currently having already some tools in the test in the manufacturing lines where we use double loading, and this will bring the wafers per hour up to 8,000 wafers per hour, which brings the throughput extremely favorable for the LPCVD compared to a PECVD tubes. For me, I think the biggest difference is on the tunnel oxide formation, where in the LPCVD we work with an in situ thermal silicon oxide, and in the tube PECVD there we need an oxygen plasma or an N2O plasma to build our silicon oxide layer. On the OPEX side, as already mentioned in the chat a bit earlier, the quartz is one of the concerns where we have cleaning cycles, and also the lifetimes of the quartz parts is between 6 to 12 months. Whereas on a PECVD, you mainly need just a cleaning cycle every 30 to 40 runs. This comes also then to the advantages. So in the tube PECVD, we have the high deposition rate and a smaller wraparound, but from our understanding so far, since there is still a wraparound, it doesn't change much, as it's more on how controlled and how uniform is the wraparound rather than how much it is. And there the disadvantages are on the tunnel oxide, which is very challenging to reach good stability and uniformity, and also on the high phosphine consumption, which needs then exhaust gas treatment, and this increases the operation costs. On the LPCVD side, on the other side, we have the thermal oxide, which has a very good quality and very stoichiometric. And also the polysilicon is very easy controllable on the grain size and the doping concentration. But as mentioned, the quartz is a concern from the market, but we believe that in the long term, LPCVD is still favorable, mainly thanks to the oxide quality, but also as we can see in the market, a lot of improvements happening for the quartz lifetime, and also on the supply chain, and therefore also on the lower operation costs. When we look at this cost of ownerships for LPCVD or PECVD, here we can see for our 4 systems or our Gen 5 systems then we can see that we already currently, with our Gen 4 systems, very similar between LPCVD and PCVD. While when we include our back-to-back loading technology, which will be mature and finally tested by in Q3 2024 to be delivered, then we can further reduce the COO of LPCVD by about 50%, which brings it to a much cheaper system than a PCVD. And when we try to simulate, we were not able to get to these numbers in the PCVD, even when we, for example, simulated with 0 phosphine consumption. When we quickly look on what next, so here, when we talk about the back contacted solar cells, there are several designs that are currently under consideration in the different manufacturers. We have the P tunnel back contact or the N tunnel back contact, also tunnel back contact with both polarities, or also designs where we get a combination of TOPCon and heterojunction designs. And from what we can see so far from the manufacturers, that independently, if they want to use etch-back or a laser ablation, most important demand so far is we want to have a stable, reproducible, uniform thermal silicon oxide, because this is very crucial on getting the back contact design running through a full production line. And here we also, from what we know so far from manufacturers that are trying to implement the XPC design, all of them working so far with LPCVD, so that they get a thermal silicon oxide and a polysilicon oxide, a polysilicon part that is very well controlled. And I can also assure you at this stage that our system is fully compatible for this polysilicon implementation in XPC cells. We have already systems that are delivered and successfully in operation in different pilot lines on manufacturer side. And with this, I would like to quickly summarize. So Laplace were pioneering TOPCon for mass production from the equipment side. And we have so far already gained experience with over 200 gigawatts of installed equipment, with now 18 gigawatts outside of China. And we were pioneering the transition to BCl3 as a precursor gas, which reduced the operation costs very strongly and made TOPCon interesting on the market. And we also have this horizontal wafer loading, which brings a better yield and a cost reduction of around 20%. And I would like to also point out again that we are very much involved in the cutting edge technology. We are in these few years now, we're already involved in 15 world records for TOPCon technology. And we are now also moving into the XPC cells, where we have already some equipment delivered and successful in operation. And with this, I just would like to share my contact details. In Europe, that's me and our sales director, Yao Sang, in China. And thank you very much for your attention, and I'm open for questions from your side.
Great, Joshua, that was a really great presentation. So one question, when you were referring to the quartz tube lifespan, you mentioned it's 6 months to 12 months. That's almost 100% deviation. So, you know, what are the conditions which will say, I mean, do you provide any best practice methods, best practices that can enhance?
Of course, with our customers, we can provide such recipes and also tips on how to enhance. There's also often on different coatings, different workarounds on the materials itself. And when I said 6 to 12 months, perhaps I have to specify that it's mainly on the quartz parts. There we see that's on the boats where we are on the above 6 months. On the tubes there we are now closer to 12 months rather than the 4 month side. But in the quartz generally, this is definitely something that we see as a concern and that we're working on it to improve the lifetime there. But we have also seen that there is already a lot of improvement happened over the last 1-2 years by small changes on the recipes, on the deposition temperatures, and also on gas flows or little tricks here and there that I will share now here in public.
And have you also accounted the downtime into your calculations? Because when you have to change the quartz tube, probably it's not not very simple, right? So
of course, this is calculated in the calculations,
and
the downtime. But we could see that the downtime is very short for the LPCVD.
And can you share some more information on your back-to-back loading, like how you are going to address the wraparound? Because when you were putting the wafers on back-to-back loading, I mean 2 wafers per slot loading, the wraparound is not uniform, right? Because it can go any direction. And how would you address this? So
it was definitely something that we were aware of and that we worked strongly with our R&D team to get it solved. Because as I mentioned with the PCVD side, the wraparound by itself, we don't see so much as an issue. We see it mainly as an issue when it's uncontrolled, when it is not homogeneously distributed, so that the edge back of the wraparound gets challenging. And there, I can assure you that we found our ways of getting the double pedal or the double loading in a way that the wraparound is not an issue.
Okay, great. Thanks a lot. It was very nice presentation. And if there are any questions, please stay back. Anyway, we will again meet in the panel. But before that, if there are any questions that are posted in the chat, please try to answer.
Sure. Thank you very much.
Thank you.